Hi, we are Group 28 and our topic is Popularity Contest. We will first describe the competition, then elaborate on our two methods, and finally share our result and conclusion. Every day, countless stray animals are overlooked in shelters. To help them, the animal welfare platform, petfinder.mine, posts the pictures online to show their charms to adopters. It currently uses a basic cuteness meter to assess the appeal of pet profiles and hope to improve the algorithm. Hence, our study will develop a model that accurately predicts the popularity score of pet photos and increases the chance of finding a loving home. For each pet's profile, we are provided a photograph and hand-labeled metadata. The dataset for this competition therefore comprises nearly 10,000 images and tabular data with binary values along with their popularity score. For unseen profiles, we will use the raw images, with or without the tabular data, to predict the score. The accuracy will then be accessed using root mean square error. There are 12 label features for each image, such as whether the image is blurred or if it is a crude picture. Before developing the model, we did some exploratory data analysis to have more insights into the dataset. We will first draw a histogram to examine the distribution of score. Notably, the majority of scores are concentrated between 20 and 45. The frequencies of score gradually decreases after 30, which is expected, but the number of score ranging from 95 to 100 is surprisingly high. This information will help us fine-tune our solution. Then we analyze the correlation between features given in the CSV file and the popularity score to decide whether the tabular data will be useful for our model training. The correlation coefficients range from approximately -0.02 to 0.02, suggesting that the examined features have negligible influence on the popularity of pet photos. As a result, further investigation and consideration of additional variables may be necessary to enhance prediction accuracy.
To tackle the popularity score prediction problem, we first decided to fine-tune well-known deep learning models on our popularity dataset. These models have shown state-of-the-art performance on image data, and they belong to two main families, convolution neural networks and vision transformers. Convolution neural networks make use of convolution and pooling operations to extract features from images, while vision transformers utilize the self-attention mechanism to learn the context and relationship of different elements in image data. The list of specific models that we have conducted our experiment on is shown here. Let's dive into the details of each model and why we have selected them for the task at hand. The first CNN model that we have selected is EfficientNet. EfficientNet, with its innovative compound scaling method, expertly balances model size and computational efficiency. The model has shown top performance in relevant tasks such as image classification and object detection, which makes it an excellent choice for our popularity prediction problem. The second model that comes from the CNN family is ResNet. Its residual connection addresses the vanishing gradient problems, which in turn help the model to achieve greater depth without sacrificing training efficiency. With its ability to capture intricate features, the ResNet architecture proves suitable for our task. Our last choice of a CNN model, InceptionNet, consists of several inception modules. Each includes several parallel parts of convolution and pooling operations of different filter sizes. With its great performance and efficiency on vision tasks, it proves to be another viable candidate for experiment. Moving on to transformer models, we'll be selecting Swing Transformer. The model architecture consists of a patch splitting module, followed by several Swing Transformer blocks interleaving with linear embedding layers and patch merging layers. It achieved top 1 accuracy on the ImageNet 1K dataset, proving its high prediction performance on vision tasks. For the experiment, since all selected models have been shown to produce state-of-the-art results on the ImageNet dataset, which includes ground truth labels of dog and cat, we predicted that they would perform well on our popularity prediction problem, which only includes pictures of dogs and cats. Hence, we decided to initialize these models with their pre-trained weights to retain the learning from ImageNet and then train them on our popularity dataset. We use TIM to access the model and their respective pre-trained weights. The challenge of this approach is to adapt the training problem of the pre-trained models to our popularity prediction problem. Our popularity prediction problem is a regression problem, aiming to predict the popularity score of a given pet's picture. However, most of the pre-trained deep learning models are trained on the ImageNet dataset with classification objectives. The output of these models is a vector of length 1000, representing the 1000 image classes in the ImageNet dataset. To fit these classification models to our project's regression objective, we employ two main strategies. The first one is classification to regression. We appended a 1000 to 1 fully connected layer, which will output the image popularity score to the selected deep learning models. The second approach is classification to classification. We converted the ImageNet classification problem to our popularity score classification problem, whereby the model predicts a picture to be one of the 100 classes, each corresponding to a discrete popularity score from 1 to 100. This is done by appending a 1000 to a 100 fully connected layer, followed by a softmax layer, which will output the image prediction probability for each class to the selected deep learning models. Finally, here is the results of our experiment. Compared to the competition's leaderboard RSMV scores, which are mostly less than 20, the RSMV scores we achieve using individual model fine-tuning are subpar. Hence, we move on from this approach and sought a more effective approach.
We attempt to fine-tuning models isn't getting good result on the leaderboard. We decided to switch our approach is to utilize pre-trained image models as a feature extractors for traditional regression machine learning methods, for example, super vector machine regressor. Here for the competition training dataset, which comprised around 9,000 images, we run inference these images through selected future models. All of these models are already trained on the ImageNet dataset. We've frozen the models, only run the inference on the competition training dataset to get selected features. We simply concatenate all the model features into one large vector. Along with these images are Q-nit score. We train a supervector machine regressor on these features along with associated label Q-nit score. Following slides are how we can get the feature from different type of models. For CNN family model, we simply extract only the artifaction of the models, right before applying fully connected layer, which used to predict 1,000 classes probability, specifically only for the ImageNet dataset. For Transformer Vision family model, similarly, we extract the hidden output state of Transformer model, a final token in last layer, as feature type encapsulating information of whole image. For clip model, we extract the feature from the clip visual encoder, also because of the training process of the clip is a multi-model, matching between the images and their text description, which will result extracted features vectors lie on the well-linearly separated space, which eventually boosts SVR performance in our task a lot.
There are over 500 models in Team Library. We use forward selection algorithm to filter the efficient models in our task. Here is an illustration of forward selection algorithm. Initially, the model begins with no features. After that, it iterates through every feature set and evaluates if this feature improves the performance, which is the mean square error of the system. If it improves the performance, we will select the feature set as efficient feature set. The process continues until there is no more feature set. After filtering, there are 52 models are chosen. If we just simply concatenate all model features, it will be extremely large. Therefore, we proceed with further group the feature set together. We run our benchmark initially in all 52 feature sets chosen. The result is summarized in this graph here. As you can see, the performance of the individual model range from 17.56 to 18.53. We divide them into 3 tiers. Tier 1, model with score less than 17.6. Tier 2, less than 17.9, and Tier 3 are remaining models. After that, we perform random combination testing, where we choose half from Tier 1, some from Tier 2, and a few from Tier 3. After experiments in 2 steps above, we derive the final set of 26 models and 1 tabular feature set across 3 different groups. After obtaining the concatenated feature from each of the group, we feed the feature into our regressor module to do regression. We benchmark 3 choices of regressor. Firstly, linear regression. Linear regression is the traditional model assume there is a linear relationship between input and output. Next one is XGBoost, which is a powerful machine learning approach using ensemble learning strategy, known for its efficiency and good performance. It sequentially builds a series of decision trees to predict the target variable, with each tree correcting the error of the previous one. This iterative process allows XGBoost to capture complex relationships in the data and handle missing value effectively. Lastly, support vector regressor, or SVR. SVR is a robot machine learning regression model. It handles noise and outlier effectively, capture nonlinear relationship using kernel functions, and prevent overfitting using regularization. As we can see here, linear regressor failed in our experiment as it can only detect linear relationship. XGBoost and SVR could capture the pattern pretty well. SVR gives the best performance in our experiment. It could be explainable due to its effectiveness in high-dimensional feature space, like 10,000 input feature dataset. As we have mentioned, we divided our set of models into 3 groups. We combine the 3 group prediction together, so we experiment with unweighted average and weighted average. For unweighted average, we simply take the unweighted average of our prediction in all 3 groups. However, intuitively, a more performing group should be emphasized more to have a larger weight. Therefore, we further explore the weighted average approach. To find the optimal solution, we use the optimized modules in SkyBi to fine-tune the coefficient K to achieve the best possible fit between the predicted and actual popularity score in training set.
So this is the final architecture that we came up with. 26 feature extractors are divided into 3 groups. The features extracted are then fed into the SVR module. After that, the results are weighted and combined into a final prediction score. The experiment results are in the chart below. First, we have the 4 best performing individual models, which range from 17.56 to 17.62. With the aforementioned groupings, the performance significantly improves to 17.01. Finally, our weighted average model further combines the results and outputs the final prediction, improving the performance to 16.95. Now we'll move on to our result and overall ranking in the competition. With our proposed model, we obtained a public score of 17.76, which corresponds to the top 2% on the public leaderboard. During this project, we have learned so many things. First, we now know about the significant impact of model ensembling, which is to combine multiple models to improve performance. Second, scaling plays a crucial role in leveraging the vast array of pre-trained models available. Third, we also found out that fine-tuning pre-trained models is not always necessary, especially for regression tasks. Last, we have learned how to deal with shifts in data distribution, which is prevalent in handling real-life datasets. In conclusion, this competition has provided us with valuable learning opportunities. We gained so much experience on coding skills as well as working as a team.